At full power, 5 F1 engines at the base of the Saturn V developed over 7.5 million pounds of thrust. In the first minutes after launch, that thrust lifted the largest rocket ever built through the lower atmosphere. But as propellant drained from its tanks, the rocket's mass was dropping at an astonishing rate, tens of tons per second. Thrust remained nearly constant. The result was an inevitable rise in acceleration. If left unchecked, that increasing G-load could have exceeded structural and dynamic limits. The solution was deliberate and precise: shut down the center engine of the first stage before burnout. It was not an emergency measure. It was a calculated decision woven into the vehicle's logic from the very beginning. This is the story of why that cutoff existed, how it worked, and what catastrophic effects it prevented.
The Saturn V's first stage, the S1C, burned kerosene and liquid oxygen for about 150 seconds. At liftoff, it weighed roughly 2,900 metric tons. By the time its fuel was nearly gone, only about 200 tons of dry mass remained. The thrust-to-weight ratio climbed from barely greater than 1 to more than 4 by the end of powered flight. Without intervention, that meant longitudinal acceleration could rise past 5G, possibly 6. Those numbers aren't dangerous for a momentary surge, but they are intolerable for a tall, flexible launch vehicle designed to carry a fragile spacecraft. Acceleration acts on every connection, every joint, and every weld in the vehicle. The tanks pressurize, structures compress, and vibration modes couple together. Above a certain limit, those forces amplify motions that can trigger oscillations or even structural failure. Shutting down one engine changed that trajectory. It reduced net thrust by about 20%, immediately flattening the G growth curve. This wasn't about comfort for the crew, it was about holding mechanical loads within the design envelope.
In the opening seconds of flight, thrust barely overcame the vehicle's weight. The Saturn V accelerated sluggishly, about 10 feet per second squared. As propellant mass left the tanks, the same total thrust now acted on less mass. The thrust-to-weight ratio climbed, and with it came exponentially rising acceleration. The structure saw these changes as compressive forces along its longitudinal axis. Engineers tracked both static and dynamic load components. Static loads came from thrust pushing upward. Dynamic loads came from oscillations, bending, and atmospheric buffeting. At the halfway mark of the first stage burn, the vehicle might already be accelerating at nearly 3G. If nothing changed by the end of burn, acceleration would exceed the design's structural limits, and the rocket's bending modes, especially those in the interstage region, would enter dangerous resonance zones. Limiting acceleration through center engine shutdown kept those bending moments beneath known thresholds. These loads weren't symmetric. The Saturn V's center of pressure, mass, and thrust vector line interacted continuously. Any misalignment generated torque, which the guidance system fought using gimbal deflection. The lower the dynamic strain, the more margin guidance had to maintain control. The cutoff preserved that balance. The F1 engine cluster used a 4+1 configuration, 4 arranged in a square, 1 at the center. Together, they drove thrust into a thrust structure of intersecting forged beams and load rings. The outer 4 engines transmitted loads both vertically and tangentially into the structure's periphery. The center engine carried its load axially, directly up the vehicle's central spine. Having that central thrust line active meant compression was concentrated along the stage's core. It provided symmetric axial loading early in flight, ideal when total thrust had only to overcome gravity with margin. But later, as acceleration rose, that very symmetry became a disadvantage. The core load path stiffened relative to the outer frame, amplifying compressive forces in the interstage adapter and lower liquid oxygen tank bulkhead. By shutting down the center engine, engineers redistributed remaining thrust toward the perimeter, balancing stresses among structural members. The four outer engines, still gimbaled for control, maintained full power and vector authority. The stage continued its burn at reduced thrust, preserving both control and integrity. Rocket structures are not rigid. They're lightly damped elastic systems with multiple natural frequencies. In the Saturn V, one of the critical modes was longitudinal oscillation, known infamously as pogo. It arose when pressure oscillations in the propellant feed lines coupled with acceleration feedback through the structure. As G-loads rose late in ascent, so did propellant flow rates and pressure transients. Higher acceleration amplified the frequency and amplitude of pogo susceptibility. The S1C stage had some damping, but its structural margin wasn't infinite. Each F1 engine included a helium gas accumulator in its liquid oxygen feed to dissipate oscillations, yet the system's effectiveness had limits tied directly to load conditions. The center engine, located on the stiffest axis, was particularly effective at exciting the first longitudinal mode. Continued high-thrust operation in that environment risked dynamic amplifications severe enough to exceed vehicle limits. Shutting it down reduced central excitation and added damping margin at precisely the time pogo risk peaked. It was an elegant intersection between propulsion logic and structural mechanics. Center engine cutoff wasn't decided by feel or real-time pilot judgment. It was determined by deterministic guidance logic embedded in the Saturn V's instrument unit. That logic was written before flight and verified in endless test series. The S1C flight sequence ran through a digital timing program in the launch vehicle digital computer. At a specific combination of propellant level, elapsed time, and thrust decay schedule, a command signal closed the center engine's propellant valves. The target window was about 135 seconds after launch, roughly 20 seconds before main engine cutoff of the outer four F1s. This timing wasn't arbitrary. It corresponded to the optimal point where thrust reduction flattened acceleration growth without sacrificing too much velocity prior to staging. Sensors confirmed proper cutoff via pressure transducers in the engine feed lines. The logic then reconfigured guidance parameters to handle the four-engine thrust geometry for the final seconds of first-stage burn. By abstract engineering terms, the Saturn V simply transitioned from a five-engine mode to a four-engine regime. The instrument unit adjusted expected thrust vectors and acceleration constants accordingly, ensuring a seamless continuation of guidance computations. The crew could see it on their acceleration indicators, the brief dip in G level precisely when designed. Had all five F1s continued running to depletion, the acceleration would have climbed beyond safe margins. With nearly empty tanks, thrust would produce over 5 g of acceleration at the moment staging should occur. The interstage structure, though heavily reinforced, was never certified for continuous compression at that level. The upper stages and payload attachments could begin to experience coupling between longitudinal vibration modes and bending oscillations from atmospheric buffeting. That combination, sustained high G along with structural flexure, could cause nonlinear structural behavior. Resonance might amplify local stresses by factors of 2 or 3. The S2 interstage could distort enough to complicate stage separation timing or cause excessive relative motion between stages. The guidance system, relying on stable inertial references, could suffer degraded accuracy as structural accelerometers registered mixed frequency inputs instead of clean, filtered signals. There was also crew survivability. At 5G sustained, astronauts could not effectively perform control actions if an abort were needed. But more importantly, the Apollo spacecraft's structural attachments were tested against defined axial loads consistent with nominal ascent. Exceeding those loads risked overstressing the SLA panels or the escape tower truss. The center engine cutoff prevented all of those scenarios simply by controlling acceleration growth. The S1C stage fed its propellants at a rate of more than 13 metric tons per second. When the center engine shut down, total propellant consumption decreased proportionally. That extended burn time slightly, but in a beneficial way. The outer four engines continued until propellant depletion, while maintaining target velocity for staging. Staging dynamics relied on a predictable sequence of forces. The velocity and attitude at separation had to match the S2 ignition plan. If all 5 engines had burned equally to depletion, the separation event would have occurred at a higher dynamic pressure and acceleration level. That wasn't acceptable for the delicate interstage ullage and ignition procedure of the J2 engines above. Center engine cutoff, therefore, stabilized the profile. It moderated velocity gain, ensured a clean interstage environment for S2 ignition, and allowed aerodynamic and structural loads to drop gracefully before separation. The trade was planned from the start, slightly lower acceleration for vastly greater structural control. The Saturn V's design reflected an engineering culture that valued predictability over raw performance. The goal wasn't absolute maximum thrust, it was controlled, repeatable, analyzable flight. Engineers sought a clear margin between expected loads and structural limits. Every major subsystem, from guidance to propulsion, worked in harmony to preserve that margin. The center engine cutoff embodies that philosophy. It's a visible symbol of system-level thinking, except a small sacrifice in thrust for much larger gains in reliability and control. Modern heavy-lift vehicles still follow the same logic. Whether by throttling engines, staging early, or cycling thrust to manage acoustic pressure, they balance power with integrity. Saturn's approach remains both elegant and instructive because it resolved complex load interactions through a single pre-programmed event. The early shutdown of the Saturn V's Center F1 engine was never a flaw. Never a shortcoming in propulsion. It was a precise act of structural preservation, a measure against runaway acceleration, coupled dynamics, and mechanical overstress. By removing one engine at the right moment, engineers protected the vehicle's slender frame from forces that could have torn it apart. The decision unified physics, mechanics, and logic. It expressed a deep understanding of how thrust, mass, and flexibility interact under high dynamic load. The Saturn V ascended not at the edge of what was possible, but within the boundaries of what was safe and repeatable. That restraint, grounded in analysis rather than spectacle, is one reason every Saturn V launched carried its payload successfully into orbit. If you enjoy engineering-level breakdowns like this, where we look at what actually protected Apollo hardware under real physical limits, consider giving the video a like. It helps more of the right viewers discover this material. And if you want to support deeper dives into Saturn V and lunar module systems, you can join the channel. Your support directly fuels future analysis. Thanks for watching, and I'll see you in the next phase of the mission.